Hello everyone, my name is Robertson Taylor and I'm a solutions architect here at Amazon Web Services. Today I'll be talking to you about Amazon Connect monitoring and how you can generate insights about call quality from agent-side telemetry data. We're going to lead by chatting about why monitoring call quality is important, a quick walkthrough of a solution that a coworker and I have made to help increase visibility into call quality, the feature set of that solution, and roadmap items we have to improve that solution in the future. So picture this. There's an emergency, a global emergency. A global emergency that fundamentally changes the way that your business operates as a whole. Your office is closing. Agents are starting to work from home, from their home networks, using a company VPN that really not that many people used before. And as a company that cares really deeply about your customers and your employees, you're trying to make sure that you still provide a really high quality of service, both internally and externally. Now, nothing's happened yet, but you want to be prepared in case that it does, and you want to be able to respond to those issues really quickly and get a full picture of the situation. I'm sure in 2020 nobody can relate to this situation, but when working closely with some of my customers, even before this year, I saw that there was a frequent demand for call center teams to have some more visibility into their network conditions. To understand why network conditions, network metrics like round-trip time latency, jitter, and packet loss can all cause some audio artifacts when using phone calls over networks. I'd have customers that would ask, how can I proactively identify and monitor client-side network changes that might cause some degradations in audio quality? So in traditional AWS fashion, a coworker and I decided to help meet that need. And coming from a software testing background, I was really happy that customers had started to ask that question because it's in line with a lot of the software testing best practices that your engineering teams probably already use. What my customers are really asking for is how they can use data to build canaries. What they wanted is a way to understand that a problem is happening, when it's happening, to actually get some real-time insights that can help them root cause a problem and figure out the underlying issue. Alternatively, if they didn't manage to notice that the problem was happening, they wanted to be able to dig through historical data and figure out the full picture. Now, a much worse situation here is one where you wind up relying on a chain of escalation from your employees, like an agent going to a contact center manager saying, hey, someone told me I sounded robotic. And that contact center manager taking that and deciding, yeah, I should escalate, and going to a network or operations engineer and forwarding along the situation. And then that engineer asking for more information from an agent. And by the time this whole process is resolved, maybe they ask for logs or to make a sample call, the problem might not be there anymore. And you might have missed your chance to get that data and prevent that problem from happening again in the future. So collecting this data on a per call and per stream basis, it should be obvious why that's really important at this point. You can use this data to generate some really interesting alarms, dashboards, and reports that can help you reduce your organizational complexity and help make your business more data-driven. Now, if you're not technical, please bear with me on this slide because it's going to get a bit technical, but we're going to shift back to business implications really soon. And the reason is to understand how we collect this data, you have to really understand how the Connect soft phone works. So in the picture on the left, we can see the contact control panel, which is the user interface that agents interact with to both take and make phone calls. There are a few different components that are necessary for the contact control panel to work. So to explore these, we'll look at a sample workflow from end to end. Let's say an agent loads a soft phone. This triggers multiple REST API requests to the Amazon Connect CloudFront endpoints. These requests range from handling agent snapshots to actually accepting calls. When an agent accepts a call, a new workflow begins, where the CCP begins brokering a session by using WebRTC. The start of this process begins by triggering some signaling requests that help each party understand the different media options that are available and figures out how to create the connection despite network conditions. So in this case, A network condition might be an agent's home machine having a software firewall that's blocking connections. After this media connection is established, the agent's network is then utilized to handle sending and receiving audio via that WebRTC media connection. So there are a lot of moving pieces there, but each has data that can be collected, aggregated, and analyzed. The gray box on the side here represents where the front end of our solution sits. There are a few libraries that are critical to making it work that are created and maintained by the Amazon Connect software engineering team. The Streams API is a library that allows you to embed the contact control panel in your own web pages. Our solution uses the Streams API to wrap the CCP. This gives us the ability to collect data on REST API requests. We then leverage the Amazon Connect real-time communications library to get hooks into the WebRTC signaling and media processes. There are a few implications of this, but the first is that we can collect metrics over an entire call and also per second level metrics about incoming and outgoing audio. The metrics we collect can include network level metrics, like the amount of time it takes to send audio to the backend, how many packets we lost in that second, and insight into how many milliseconds of data were stored due to network congestion. We also have information about individual agents, like their routing profiles or the queue that the contact came from. In our solution, we ingest and store this data by creating a serverless backend. By creating a serverless backend, we ensure that we can handle requests even at peak volume and pay only for the compute time that we use. The serverless backend then forwards this data to Amazon Elasticsearch. The Amazon Elasticsearch service piece gives us the ability to search through the data to do historical analysis and also access to Kibana, which is a user-friendly interface that can assist in configuring alarms, searching, and even establishing dashboards. We also have the ability to aggregate this data based on the fields that are present in the individual records. So one example that we have is, in our solution, we do queue-level aggregation that can show you the difference in data across queues. And you can see an example of a visualization that does this on the top right. There we see the round-trip time average based on different queues. So the teal queue represents the basic queue, and the red queue represents the sales queue, while the yellow is the global average. And we can see that there's a huge disparity between these two queues. Now, all of this data is mocked to help exaggerate an example, but this might be a reason to bring in a network engineer and say, hey, can you figure out why there's a 400 millisecond difference in latency? So you can also modify this a bit to fit your use case. So maybe your organization has Amazon Connect routing profiles that are configured on a per-site basis. And in this case, that might look like having agents in Sydney with an individual routing profile and agents in Melbourne with another routing profile. You can then aggregate based on that routing profile to get site-level metrics that can tell you how networks are performing at different geographic locations. For a deeper look at the solution, we'll evaluate how it works from end to end. Deploying the solution is really simple. It's a single click from the serverless application repository, which deploys CloudFormation stacks to your account. After deploying the stack, agents can access a custom website by using Amazon CloudFront. This CloudFront distribution serves content from S3. We use CloudFront to make sure that we have local caching and regions that might be far away from the S3 bucket. After the web page is loaded, we start to use API Gateway. So the way that we use API Gateway is by sending 30-second batches to the API. That API then invokes an AWS Lambda function that transforms the data into per-second level data and enriches it with context level attributes. After the transformation, the data is then bulk uploaded into Amazon Elasticsearch. All of this is done transparently and doesn't impact the agent experience. Contact center administrators and operations specialists they do have a different experience where they access a Kibana URL and then sign in with Amazon Cognito to make sure that only people who should have access to this data do have access to the data. From there, they can search through data, create their own visualizations or aggregations, or view our preconfigured dashboards. For a bit of information about our preconfigured dashboards, it's really important to note that we've created these with two different personas in mind. We understand that network engineers and operations specialists probably care about a lot different fields than business users do. So we've tailored our data and our visualizations to make sure that this is kept in mind. For instance, a network engineer might care about network level statistics, or the address of the server handling the media, or the private IP of the agent. They can filter records that they see by using a drill down dashboard that we've created that provides investigative fields that can be used as filters, like a contact ID or an agent name or a queue. There are other metrics there as well that you can filter by, and you can extend that to even include custom fields that you provide. You can go even further and search through the entire record set using keywords or trying to isolate via private IP. The solution provides all the tools you need to do this in-depth investigation. Now, all of that probably sounded really irrelevant for business users who might not have the domain knowledge to understand at what point latency becomes an issue, or at what point a combination of packet loss and jitter might cause some audio artifacts. Taking this into account, we've created some dashboards that show important metrics like the call duration below a minute, or the number of calls with failures, or even the total number of calls with significant packet loss in either direction. All of these could be prompts for the contact center administrator to start kicking off an internal investigation, or you can even use this to create a support request to AWS Premium Support for some further guidance. In both cases, the data that's been stored in AWS, or stored in your AWS account and Amazon Elasticsearch service, is extremely relevant. The last piece to mention here is this solution's really extendable. Kibana visualizations are very simple to create, and the front end can be modified to add your company-specific fields that you need for analysis. With a bit of development effort, you can really tailor it to your needs as a customer, and all the code is open source, and it's really extensible. In line with that, we do plan on iterating based on your feedback. So from some early comments we got from customers and technical account managers, we started working on 2 new features. The first is adding some functionality to our custom CCP to give agents visibility into their own network conditions. Through some prescriptive guidance on acceptable network metrics, we were planning on adding some red, yellow, and green indicators to show agents when they might be experiencing issues, and to allow them to proactively respond. At a per call level, that might mean asking their customer if the audio quality is fine, or asking them if they can be understood, or asking if they should be transferred to another agent. All of these can help improve the customer satisfaction for customers who might be a bit shy about complaining or might otherwise just hang up. This can also be used to kick off that process we discussed before about notifying call center managers and to help isolate regional trends. The next feature that we're talking about is using the anomaly detection release from Amazon Elasticsearch service. The recent anomaly detection feature uses a random cut forest algorithm to help identify potential anomalies in arbitrary data. So in our case, we can use round-trip time, packet loss, and jitter as a set of features and detect anomalies across this set. So random cut forest algorithm allows us to use unsupervised machine learning, which means there's 0 effort on your part, to classify this data within individual time windows and look for anomalies. In the chart to the right, you can see an example with anomaly detection that's been trained over a period of days on our data to help isolate spikes in round-trip time latency. You can see from the teal curve there that the confidence of the detector is increasing over time, and the number of anomalies that are detected are decreasing. But from the graph, you can see that the anomaly grade of those that are detected are the actual spikes in latency from the detected anomalies are a lot higher. Before, you can see that some minor spikes in latency were triggering anomaly detection, and you can see that after the training is completed, we start to have a lot more reliable results that are detecting a lot more significant anomalies. I'm really excited to see how this can help simplify operations for teams and how customers can get some near real-time notifications on changing network conditions across all of their agents' calls. I look forward to your questions, and please feel free to ask away. Thank you for your time.